All right, y'all. So next unit, we're in chapter 5, and this is 5A. And so here's the College Board videos if you want to go and look at those. Okay, so this unit is actually not anything new. So we are going to revisit the normal distribution in terms of continuous random variables. So the unit that we just finished, unit 4, we talked about discrete random variables. And remember, discrete are whole numbers. So we had whole number values, so we could say what's the probability that something equals something, right? So now what we're going to do is we're going to talk about continuous. And remember, continuous variables can be fractions. So they can be fractions or decimals. So it says continuous random variable is a variable that can take on any value within a specified domain. So every interval within the domain has a probability associated with it. Okay, so continuous random variable with a normal distribution is commonly used to describe a population. And we're going to get more into populations and samples, but right now we're going to just talk about this normal distribution and a population. Okay, so the area under the curve over a given interval represents the probability that the particular value lies in that interval. So this is not anything new. What is new is that back in Unit 2, we talked about area under the curve in terms of a proportion or a percent. And now what we're going to do is we're going to talk about the same area under the curve in terms of probability. So when we see this probability statement, it says probability that x is greater than little x. So this big X here, this is our random variable. So we're not changing our terminology with variables. This is our random variable. And this x sub a, this is where we want, this is the area that we're looking for. Okay, so it says here, the probability a randomly selected variable is less than x sub a. Now we're assuming this normal distribution. So just kind of a little review. This is what our normal distribution curve looks like. And we have our mean that's right here. And then this would be our standard deviations would be going out 1, 2, and 3 standard deviations. Okay, so this question says the probability that a randomly selected variable is less than x sub a. So if I have some value, and it doesn't tell us where, but I'm just going to say this is x sub a. And if we want to know the area that's less than that, that is this area that's underneath the curve. Okay, and again, we're looking at probability, which is the same as percent, which is the same as proportion. But in this case, all we care about right now with our random variables is probability. Okay, so this next one, our random variable lies between two different values. So what does this look like? So we're going to say this is our x sub a value, and we're going to say this is our x sub b value. And so if we look at the probability laying between these two regions, it would look like this. And it's important to know that x sub a and x sub b do not have to be symmetric. All right, so then we go to this last one, the probability that a selected variable is greater. So we have this value right here, and we're going to say that this value here of x sub b, we want to know the probability that's greater. So it's going to look like this. So we go back to drawing our normal curves and then the area associated with, or the probability that fits the area that we're associated with. Okay, now a couple things that are different with continuous random variables. So this says the probability that x equals x sub a. So if I draw this, and I have, it can be anywhere on here, so I'll just say that this is x sub a, and we want to know the probability that x equals x sub a. So we're basically saying, what is the probability that this hits this line? Well, what happens in this case is it's 0. And so this is why we look for intervals. So we're saying at this exact point where x sub a equals x, there's no probability associated with that, and so we want to look at an interval. And it might be just this little tiny interval on both sides of it, but we want to look for intervals. Okay, so because of that, this says the random variable x is greater than or equal to x sub b, and this is the same as the probability that x is just greater than x sub b. And we know this because we just said that if x equals x sub b, that this is 0. So it doesn't really matter if we have greater than or less than and just greater than or less. So hold on, rephrase. It doesn't matter if it's greater than or equal or less than or equal or just greater than or less than, because those are going to be the same thing. Okay? So just like everything else, we have to, as we go through and solve for these normal variables, we're going to look for a few things here. So the first thing that we're going to look for here is that we want to communicate what the random variable is in the distribution. And then we're going to calculate. So we're going to calculate what we need, right? And then we're going to create our curve or our distribution. And then the last thing here is we're going to communicate again. I'm going to change this C to conclude. So we have 4 different C's here. We have communicate, calculate, create, and conclude. So those are the 4 things that we have to make sure that we account for when we're dealing with normalizing random variables. Okay, so let's look at this example. It says the height of young women follow a normal distribution. So that's key. It tells us this right now. With a mean height of 64 inches and a standard deviation of 2.7 inches. If you were to choose one woman at random, super important, what is the probability she is less than 63 inches? Okay, so here's what I know. I'm going to talk about all of this, and I'm going to say that my random variable x right here is going to be the height of women, I'm going to say young women in inches. All right, and it tells us it's a normal distribution. So what I can say here is that x, our random variable, is approximately normal, and I know that it has a mean of 64 and a standard deviation of 2.7. Now remember, this is our nomenclature that tells us it's a normal curve already, okay? So we can go over here and we can say the mean in the x variable is going to be 64 inches, and our standard deviation with our x variable is going to be 2.7, but because it tells us it's normal, we can just go straight to this guy, okay? So now we get to the calculate. So write down our probability statement and convert to a z-score. So my probability statement here is that we want the probability of our height of young women to be less than 63. So this is my probability statement. All right, now this is required. We have to convert this to a z-score. So what this looks like, and if you remember, I'm going to put this back over on the first page where we have all this space. So my z-score is going to be my value that I'm looking for minus my mean over my standard deviation. So I know it's been a fat minute since we've done z-score, but this is what we're looking for, okay? So let me go back over here. So when I do this, I want the probability that my z-score is going to be less than, this is my calculation, of 63, that's what I'm looking for, minus my mean over my standard deviation. Okay, so if I plug this in my calculator, I get 63 minus 64 divided by 2.7. Okay, so my probability that z, it's not x anymore, z is less than 63, is going to, that's wrong. Hold on. The probability that z is less than 63 minus 64 over 2.7 equals negative 0.3704. Okay, so that's my z-score. So now what I want to do is I want to create my probability curve, and then I'm going to use technology to actually solve this. So here I have this normal distribution. And with this normal distribution, because I created a z-score, that means that this value here is 1, and my standard deviation is going to, oh my gosh, y'all. My mean is going to be 0 for my z-score, and my standard deviations now are going to be 1. So just a little review. If we went back up here and we use these values, we would say that our normal curve, right, would be 64, and my standard deviation would be 2.7. So this direction, I would go 66.7, and this direction would be the subtraction of that. But because with these probability curves, we're going to go to a z-score. Z-score, remember, means we've standardized it, so our new mean becomes 0, and our standard deviation becomes 1. So if my z-score is negative 0.37, that's going to be a number that's going to be in here somewhere. So it's less than 1. So here's where this is, and this value here is negative 0.3704, and I want the area that's below that curve. All right? So here is my normal distribution, and what I want to do now is I want to look at this and I want to find the value of my z-score being less than negative 0.3704. And to do this, I'm going to do this using my normal CDF. And if you remember, we've been using PDF for geometric and binomial, but when we look at the normal graph, we always use normal CDF. So if I look at this, my lower bound here is going to be negative infinity, and my upper bound is going to be my z-score, so negative 0.3704, and then my mean is 0, and my standard deviation is 1. So if I go here to my calculator, and I go to my distribution, and I go to normal CDF, that's my negative 0.3704, mean is 0, standard deviation is 1. So this gives me a value here of 0.3555. Okay, now what this is saying is this is my probability. So now when we go over here and we do our conclusion, so write a sentence communicating the answer, so this is the conclusion, I'm going to say the probability that a randomly selected young woman is less than 63 inches tall is 0.356. Now, what this also means, and I don't have to say this, this is my probability statement, so I'm good there. But what I can also say is that 35.6% of women are less than 63 inches. That's what else this is saying. Okay. All right, let's work through another one. So I'm going to work through another one that's not going to be all boxy here where we've got these different pieces, but those are the pieces that you're going to need as you solve these. So let's go to this first one. The heights of young women follow this normal distribution with a mean height of 64 inches and a standard deviation of 2.7. So nothing's changed. If you were to choose one woman at random, what is the probability she is greater than 66 inches tall? Okay, so I'm not going to go back up here and define my random variables because this is all the same. But what I'm looking for right now is I'm looking for the probability that my random woman is greater than 66 inches tall. And so to do this, we know that we have to convert this to a z-score. So the probability that z is going to be greater than 66 minus 64 over 2.7. Okay, and I've already done the math on that, and I know it's 0.7407. So I can rewrite this and say the probability that z is greater than 0.7407, this is what I'm looking for. This is the question that I really want to answer now. Okay, so I have to create my curve. So what I've done is I've calculated. So now I create this curve, and I know that this is my standardized mean of 0, my standard deviation of 1. So this value that I have right here now is 0.7407, and I want to know the value that's greater. So I want that part of my curve. Okay, so now what I'm going to do is I'm going to write the calculator speak here. So I'm going to go back to normal CDF, and this time my lower bound is going to be 0.7407. That's the lower bound, and my upper bound is going to be infinity, and my mean is going to be 0, and my standard deviation is going to be 1. So if I plug this in now, I have 0.7407, and my upper bound, and what I get here is that this value is 0.2294. All right, so last part of this is my statement, and what I'm going to say is the probability a randomly selected woman is greater than 66 inches is 0.2294. All right, so let's go on to this next one. So same question. The only thing that this is changing is that it says, what's the probability she's between 64.5 and 70 inches tall? So again, if I look at my curve right here, I want to know this time we're going to be between two different values. So what I have to do is have to convert this again to a z-score. So here's what this is going to look like. The probability that she's between 64.5, this is my random variable x, and 70, and I'm going to convert this to a z-score. So this is going to be 64.5 minus 64 over 2.7. And now this variable becomes my z, my standardized score, and I have 70 minus 64 over 2.7. Okay, so I just plug that in, and I get the probability of 0.185 is less than z is less than 2.22. Hold on, I'm going to check this one real quick. 70 minus 64 divided by 2.7. Yeah, 2.22. Okay, so if I have 0.185, that's going to be right here. So just almost past 0. And I'm going to go up here. It's going to be past 2 standard deviations. And this value here, so 0.185. And this is 2.22. And so here is the region that I'm looking for. Okay, so again, my normal CDF, my lower bound is going to be 0.185. My upper bound is 2.22. And then I know my mean and my standard deviation. So that hasn't changed, right? So if I go in here, and this tells me that this value that we're looking for here is 0.4134. Okay, so just to save time, because the conclusion is going to be the same as what we've had. So the probability that a randomly selected woman is between 64.5 and 70 inches is 41.34. Okay, that hasn't changed. Okay, so the best news is this is also not new. So we are combining normal random variables. So we have just finished the section where we did combining random variables in chapter 4. And so the good thing is if it tells us it's normal, then when we combine 2 or more normal distributions, the result will become a combined normal distribution. So if they're already normal, both variables, so in this case we're going to have x and y, then the combined is also normal distribution. All right, so just like we did with discrete random variables, if my expected value or my mean of 2 random variables is added, then this is going to be the same as the expected variable in x and the expected variable of y. So remember, this is 2 different things. So maybe it's men and women. All right. Same thing here when we're subtracting our means, the mean of x and we subtract the mean of y. That has not changed. Okay. E of x is also represented as u of x. Or if I said e of y, this would be the mean with my little subscript of y. Okay. So our spread, our standard deviation, this has also not changed. So it is the square of the variance of x plus the square of the variance of y. Remember, the standard deviation is the square root of the variances. And whether it's addition or subtraction, my formula doesn't change. The square of x, the variance squared in x plus, even though this is negative, we're adding the square of the variance. Always add the variances. Okay, now what we didn't say here is that the random variables have to be independent. We've already gone over in our BINS acronym that I, we have to show independence. It's the same thing here when we're combining random variables that are continuous. And so why are we combining? So we are combining multiple normal random variables to basically make new distributions. Now, what does that look like? So this is a perfect example of why we do this. So it says, in a 4x100 track relay, 4 team members each run 100 yards. Their combined total time is their finishing time. Suppose the times taken by each runner to complete the respective legs of the relay are independent of each other and follow a normal distribution with the following parameters. So here are my 4 runners, and over the course of the season, here's their mean times, and here are their standard deviations. Okay? So, my question is right here, and it says, what is the probability that the total time taken by the team to complete the relay race is between 42 and 46 seconds? So, probability is going to be between 42, and I'm just going to use x, and 46 seconds. Okay, so remember, the first thing here is communicate. So here's my probability statement, but I have to define my x variable. And this is going to be the total time to complete the race. And I'm going to go ahead and say that this is going to be in seconds. Okay, now the other thing that I know about this is that it tells us on the other page here that all of the runners follow a normal distribution. So what I know here is that my random variable is going to be approximately normal, but what I don't know are the values that are going to go in here. And this is what I have to calculate. Okay, so the first thing is I need to know my expected value of the mean of all of this. So this is going to be this is going to be an equal sign. Runner 1, hold on, let me change that. Equals runner 1 plus runner 2 plus runner 3 plus runner 4. Okay, so this expected value is going to be these means that I have over here, and let's look and see what this is. 12, 11, 10 and a half, and 11 and a half. So 12, 11, 10.5, and 11.5. So my expected value, my expected mean of this is going to be 45 seconds. So if this is my expected mean, right, these are all of my means. If I add them all up and I know they're normally distributed, then my mean of this distribution is going to be 45. So now I want to find the standard deviation of this distribution. And the standard deviation, remember, is going to be the square root of each of my standard deviations squared. So 1.8, 1.2, and 1. So I'm going to write this all out, even though some of them are pretty silly. I don't need to really do 1 squared. And then I have 0.8 squared plus 1.2 squared plus another 1 squared. So remember, it's the variance. So if I look at this, I get the square root of 1 plus 0.8 squared plus 1.2 squared plus 1. So 2.0199. So standard deviation is 2.0199. So that's the value that I'm going to have over here. 2.02, just to keep it short. Okay, so I've communicated. I've started my calculations, but I need to finish my calculations. So remember, here at this point, I have to go to a z-score. So I'm looking for the probability that I have between 42 and 46 seconds. So if I can convert this to a z-score, it's the probability of 42 minus 45, because I'm using my new mean, divided by my standard deviation, and that becomes my z-score. And then my maximum would be 46 minus 45, and that is over 2.02 again. Okay, so I'm going to write this here. I haven't done this math, so I need to do this real quick. 42 minus 45. So I get negative 1.485. And that end of it is 0.495. Okay, so here is my probability distribution. So I know that it's normal, so I'm going to draw my curve here. This is 0, -1, -2 standard deviations, and 1 standard deviation. It'll all fit in there. So this value here is negative 1.485, and I'm going to this value right here, which is 0.495, and I want to know the value in between those 2 points. Okay, so I'm not going to write down my calculator speak. I'm just going to go ahead and put it in here. So my lower bound is negative 1.485. My upper bound is 0.495. My mean and my standard deviation are 1. And so this gives me a value here of 0.6209. Okay, so what this is saying is that the probability, let me go back up here to my statement. What is the probability that the total time taken to complete the relay races between these? I would say that the probability that the team finishes, so the probability that the team finishes between 42 and 46 seconds is 0.6209. Okay, I'm going to save some time by not writing that down right now, but I'm going to say it one more time. The probability that the team finishes the race between 42 and 46 seconds is 0.6209. Okay? All right, so subtracting, this next question here, we're talking about subtracting normal variables. So let's look at this. It says you're managing a manufacturing process that involves 2 sequential steps taken at the same time. The 2 processes work independent of each other, and the time taken to run each step can be modeled with a normal random variable representing the processing time. Process 1 has the stats, process 2 has these stats. You need the difference in processing time to be less than 10 minutes. So difference in processing time to be less than 10 minutes for a critical operation. What's the probability that you meet this requirement? So here's what I'm going to do. I'm going to say that X is going to be the process time for process 1. And Y is going to be the process time for process 2. Okay, and what I know here is that the mean for process 1, if I come up here, is going to be 25 minutes, and the standard deviation for process 1 is going to be 5 minutes. The mean for process 2 is going to be 20 minutes, and the standard deviation for process 2 is going to be 4 minutes. Okay, so here's the stats that I have. Okay, so what I want to know is the difference in processing times. So the first thing that I know is because it tells me that they're normal, I can say that the process time for 1, which is going to be my X variable, is approximately normal, and my values are going to be 25 and 5. And that I can say process 2, which is my Y variable, is approximately normal, and those values are going to be 20 and 4. So what I want is the difference in processing times. So I want the probability that X minus Y, so this is the difference, processing time 1 minus 2, is going to be less than 10 minutes. Okay, so for me to figure this out and actually come up with the z-score, I need to come over here and calculate what my difference is. So the mean of X minus the mean of Y is going to be 25 minus 20, which is 5. And my standard deviation of x minus y is going to be the square root of 5 squared plus 4 squared. And that is going to be, I don't know, let's figure this out. Square root of 25 plus 16. Oh, duh. This is going to be 6.403. That's my standard deviation. Okay, so now I can rewrite this because what I have here is x minus y is approximately normal. And now I have a mean of 5 and a standard deviation of 6.403. Now, remember, this is my difference. It's not the mean of both of these. It's the difference of x minus y. So it's not like I added these up here, and that's why it's not 45. It's the difference. So if I'm looking for this probability of x minus y, and I know that my mean of x minus y is 5, and my standard deviation is this, I can find my z-score. So now what I have is the probability of x minus y is less than 10. We don't need that again, but I'm just going to write this. This is the probability that the z-score, which is going to be, 10 minus 5 over 6.403 is going to be 0.781. Okay, my value minus my mean or my standard deviation. So this is my z-score. Okay, so I can draw my distribution at this point. So I have this point here at 1, and this is my value 1. So at right here, 0.781, I want to know processing time is less than, so it's everything to the left. All right, so if I plug this in, I'll just go ahead and put the calculator speak down. So my normal CDF, my lower bound is going to be negative infinity. My upper bound is going to be 0.781, and then I'm using 0 and 1 for my mean and my standard deviation. So let's look at this. So what we get is a value here that is 0.7826. All right, so I'm going to go ahead and write my statement. The probability that the difference in process times, and I'm going to go ahead and say P1 minus P2 so I know which one went first, is less than 10 minutes is 0.7826. Okay, so probability in the difference being less than 10 minutes is 0.7826. Now, one of the things that we haven't done at all in here is we have converted everything to a z-score because for probability, they want to see this. They want to see these z-score calculations. But what we did with area is we went in and we said, okay, we don't necessarily need to convert this to a z-score. And so if I look at this is pretty interesting. If I go back in here and do normal CDF, and I look at any of these values, this one's a little harder because it's asking for a difference, but let me pull back this guy. So here's the one where we had the ladies are between 64 and 70. So if I use my normal, my lower bound at 64.5 and my upper bound at 70, and I'm using my mean of 64 and my standard deviation of 2.7, and I plug all of this in, I still get the same value, 0.4134. So we did this back when we did area and proportions of normal graphs. We said, okay, just put in your lower bound and your upper bound, but with probability, they want to see the z-score. So make sure you've got that part, okay? This last page that's here in your notes was going to be partner practice in class. So go ahead and do that. I'll post the key for this online, and then you can go back and check it if we don't have time to do it in class. Okay?